and here I have two features, two parameters. One of them is rectangularity, and the second one is circularity. Okay, so that is what I obtain for example for the rectangular object, and again for triangular object. So I obtain this one. So now I have these two parameters, and with that, okay, so I can have a selection using this in the space parameter. So here, as I have two parameters, so the space is a 2D space, two-dimensional space, which is rectangularity in function of circularity. Okay, so that is a very simple example. So here we have only two parameters, but we can have a lot of parameters, not only two, maybe 10, 100, 1000, and so on, okay? And with all these parameters, so we can use the classification. Here it's a very simple classification, as you can see, okay, because it's a linear classification, okay? So if we have more, here in this area in regards to this line, so we can affirm, so we can have the as a detection, we can say that here in this area we have always rectangular object, okay? And at contrario, we have here the triangular object here. Okay, so just to go now to okay, here, okay, so that is what I mean by classification. Okay, so here, for example, we could have only two parameters. Okay, so here, what means in fact classification? So the classification, it means that here, so we have to define, okay, a performance. Okay, on my simple example, for the recognition, in fact, rectangular object and sorry.
Yeah.
You have some trouble? No, no, it's okay. Okay, so here we have the classification. So, and in fact, for example, if I use again the simple example with triangles and rectangular objects, okay. So in fact, the question is the performance, okay. So if we are with a very simple there was some noise. No, it's okay now. Okay. Sorry.
Tolong mahasiswanya dimatiin semua mic-nya ya. Mic-nya dimatiin ya. Tolong semua mahasiswa mic-nya dimatiin ya. Dengarin Prof Michel mengajar.
Oke.
Vas-y Michel.
Oui, okay, thank you. Terima kasih. So here we have the performance, okay, with a simple example with triangles and rectangular objects. So the performance was, for example, 100%. It's perfect, okay? But in the real life, it's not the case, because to obtain 100% of success, okay, it's very easy with very simple objects, but in the real life, we don't have simple objects, okay? We have complex objects to recognize, to classify. So it means that the performance sometimes it's 90%, 95%, and so on. So we have some errors, and we need, in fact, to measure the performance of the classifiers that we have. Okay, so here we have to do that. So we have, in fact, what I mean is here with a learning database. For example, with a learning database, so we send to the classifier a lot of examples. For example, a lot of rectangles, a lot of triangles. Okay, that is just to in fact, to have a lot of examples about that. And after that, okay, So we can learn our classifier to obtain, in fact, the results. And to measure, in fact, the performance, what we do, so in general, we use the majority of the data for the learning. So the average of the amount of data is 90% here. And here we use from this database, from the original database. So we use, in fact, 10% of data, something like that, okay? Okay, so now just an example. So because we don't have always simple triangles and simple rectangular shapes, okay? So another first example is this one. This one is a very famous database. In fact, here, so we have the idea is to classify if we have 0, 1, 2, and so on, and 9. Okay, so in fact is to recognize, to classify and to recognize the 9 digits, which are the 10, excuse me, digits which are here, because 10, because we have 0, 1, and so on until 9. Okay, so what we have inside this database, so the name is MNIST database. It's from the US, but in fact it was developed maybe 30 years ago by Lequin. Lequin, I remind you, is a French, a very famous French researcher, but who is in charge of artificial intelligence in Facebook. So he's located in the US, okay? But he developed 30 years ago this database, okay? So this database is public, okay? So we can use this database by ourselves, okay? So you can see if you write MNIST database on Google, so you will find directly this database, okay? So it looks like that because, in fact, as you can see, it's 0 and 1 here, so it's similar to handwritten American digit, okay? And that is what we have, okay? So the idea is to recognize all that. And what we have inside this, in fact, this database, so we have, in fact, 70,000 digits. We use 60K digits, and we keep for learning, okay? And we keep 10K digits for the test, okay? So the idea is, it's like a professor and children, for example, who are learning how to read or how to count, okay? So the professor, the teacher, learns to the child, okay, so you have to, if you have to count, for example, 1 plus 2 equals 3, okay, so that is a lessons, okay, and he teach all the rules to do that, okay, and after that, that is an exercise, and the exercise means the test, okay, and we test, in fact, the child or the children, if they are able to do that, okay? Okay, that is the same here with artificial intelligence. So we teach, so we learn, and after we test. Okay, so it means that if we have, for example, 60K digits for the full database, so it means that we have the average is around 6K digits per 6K example, excuse me, 6K example by digit. For example, we have 6K example for 0, 6K for 1, and so on. Okay? So with that, we can learn our classifier and after to test with this one, okay, what is the performance. Okay, so here that is some, in fact, some metrics that we can use, okay? And so the performance measurement, so we have a very famous metrics about that, okay? So here we have, in fact, 4 possibilities for the classifier here, okay? So it means that if it's perfect, so we send, for example, digit 0, and the output will be 0. So here it's perfect. So it's what I mean is a true positive. Okay. Now we can have the here the true negative. Okay. So it means that we are false positive first here. Okay. So it means that here we send, for example, 0, and after that we obtain, for example, 1, 2, or 3. So it means that we made a mistake. Okay. And after that we have true negative and false negative. It means that we never recognize the digit. For example, we send 0 and we don't recognize the 0. Okay, so we made a lot of mistakes. So in fact, what we do, we can measure the two metrics. The first one is the precision. So that is in fact this equation. So we divide the true positive with true positive plus false positive. Another matrix is a recall, and that is this one. Okay, and after that we can measure the full, in fact, performance, the full score of the classifier, and in fact, that is obtained with this equation, which is here. Okay, so how do we obtain true positive, true negative, and so on? So for each try here, so we send, for example, first time 0, we obtain a result, okay, and so on. So, and we do that with 10% of the database, okay? So it means that here we send the 10K digits, and we can measure how many times there are mistakes and so on. So it means that we obtain true positive, false positive, and so on. Okay, so we can measure the performance here. Another metric that we can use, which is very famous also, the ROC curve. Excuse me. ROC means that it's a receiver operating characteristics. What do we mean with that? In fact, excuse me. Okay. So it means that we have to measure the true positive in regards, in function to false positive. So in the ideal solution, it should be, in fact, maybe I don't know. It's me. There is an echo. Can you hear?
Pardon, sir. Someone forgot to unmute, to mute.
Okay, no problem. Okay, it's okay now. Okay. So here, so we have the ideal solution, but it never happens. Okay. In fact, it should be 0 false. Okay, it's perfect. And in fact, we have 100 times with a true positive, and we never have false positive. So it's very difficult. Okay, sometimes it could arrive, but it never arrives in the real life. Okay, even for the human people. Okay, so we do mistakes. Okay, and okay, so the idea is means that generally we try to arrive to this one. So maybe here, for example, we are at 90% or 95%, and we have few false positive. It means that, for example, if we are with the MNIST database, is that here, so we have maybe here, for example, 95% of data are okay, but 5% or maybe 1 or 2% here are false. Okay, so it depends, in fact, how many false positive can we accept in the application. and at minimum, what is the true positive that we want to obtain. Okay. Okay, so generally we try to have this kind of curve. Okay, and here, as we can see, we have the random classifier, because it means that 50% of the time it's a true positive, and 50% of the time it's in fact false positive. So with that, it's the classifier does not work, so it's random. Okay, so in fact we have to be more than to this one. We have to be on the left part here, and ideally here. So that is the second, in fact, metric that we have is the ROC curve. A third one, which is very interesting, is in fact the matrix confusion. Okay. In fact, for example, if we have only two categories to classify, so for example, if I want to recognize A and B characters, as I presented in my first lecture, for example, so here we have only two categories. In the MNIST databases, we have 10 categories. Okay, so here we have only two. Okay, so it means that the definition of the matrix confusion. So it means, what I mean here is here that is what we obtain with artificial intelligence. So in other words, with the classifier. Okay. And here that is the expert. So we know the truth, the exact truth. Okay, here. Okay, that is in fact what we have to obtain. So here we are with the true positive. So we with the classifier here. So we say yes, and okay, the answer is yes. Okay, with the false positive, we see here that with our classifier, we say no. And here, the expert, the answer is yes, okay? And so on, okay? So we have false negative and true negative, okay? So here, we never find the good solution, and here is the same here. Okay, so that is just the definition of the matrix confusion. We can see some example here. So ideally, that is what we obtain. In fact, that is what we obtain here. And as you can see here, so we have the true label. It means, in fact, it's the expert, okay? And here, that is what we obtain with the classifier. So with this example, that is a normalization. So it means that here that is in percentage. Okay, so maximum is 100%, and here, so that is what I mean with normalization. Okay, and here it's without normalization. So it means that how many times so we obtain this one and so on. Okay, so generally we use in fact the confusion matrix with. Excuse me, it's not without, it's here, it's a with, there is a mistake, okay? Okay, so here, so we can find that, because here, so we see that, for example, that is the result that we can obtain for the MNIST databases with a simple classifier. We can see that the 75% of the time, we say, here we say 0, and okay, it's 0. But here we have some false positive, because here, in fact, we say 0 and the true label is 1. So it happens 13 times, 13% of the time, okay, and so on. So ideally, it should be to have, in fact, an identity matrix. So it means that in the ideal case, if the classifier is perfect, so normally we do have 100% here, so 100 here, 100 here, 100 here, and so on. So as we can see here that this classifier is not so bad, but here there are a lot of mistakes between here, this one and this one, okay? So we have to correct this one, okay? So this matrix confusions help the designer, okay, so help the engineer to correct the classifier. So it means that we have to modify the parameters of the classifier, but also maybe we have to add some other examples in the databases. Okay. Let's see now some example of classifiers that we can use. So here that was the definition of the metrics, how to measure the performances of the classifier. So now let's see some basic classifiers. So the first one is linear. So we have already seen the linear when in the previous lecture I spoke about how to recognize a rectangle and triangles. Okay, it was linear, and I spoke a few minutes about that this morning again. Okay, so here we can have, in fact, with one parameter. So it's what I mean. It's linear. Here I have three categories. Okay, C1, C2, and C3. So it means that if we are at the left of this first threshold, so we are in this category, okay? Here we are on the middle, and here on the second category, and when we are at the right of this threshold, we are on the third category. For example, that is very easy to do that with, for example, if we want to measure the temperature, so it means that here, so if, for example, here it's 10 degrees Celsius, it means that here under 10 degrees Celsius, we are in the cold temperature. Here, if we are at 30 degrees Celsius, okay, so it means that between 10 and 30 degrees Celsius, it's a medium temperature. And here, if we are more than 30 degrees, here, so we can say that it's a hot temperature, okay? So in fact, when we are just reading at a thermometer, so we do that from a long time. Anybody do that, okay? So we have the thermometer, so we can do linear classification, okay? So the problem is that sometimes there are some mistakes, and the problem is, in fact, the accuracy, because sometimes there are some mistakes when we are just in this area, okay? If we are here, so we know that we are sure that it's, in fact, the medium temperature, but if we are here or here, it depends, in fact, of the accuracy of the threshold and so on. Okay, so that is what I mean with only one parameter. It was the example of the temperature. Okay, now we have second examples that it's the same examples that I use for how to classify. So here we have only two categories. For example, in this example, rectangular or triangle. So it's not in the same direction, but the idea is the same. And we have two parameters here, so rectangular, and here, for example, it should be circular. Okay, so in fact, with this one, so we have rectangularity, excuse me, and here circularity. Okay. Okay, so with that, so we can separate the space here. So if we are in this area, it's a C1 category, and otherwise here we are in the C2 categories. Okay, so for that we can use n parameters, as I explained before. So it's parameters and not parameter. Parameter is French word, but it's very similar, very close to the English word. It means it's a parameter, okay? Or features, as I explained. So as I explained in the previous lecture, here we have with the Freeman algorithms, shapes algorithms, and shapes analysis and texture analysis. So we can have n parameters, okay? So and in fact we can do with all these parameters we can do linear in fact classification. So again, this linear classification works with very simple application, like temperature, okay, classification, like, for example, very simple shapes, like rectangular shapes or circular shapes, okay, but or triangle shapes, okay, but in the real life, again, linear classification cannot work very efficiently. So the idea is to use some others. Another one, which is very interesting, in fact, is KNN. KNN is means that K nearest neighbor. Okay, so here it's again the translation in French. Okay, here is an English word, means that with when we speak about KNN, okay, and KNN in fact is a very famous algorithms, in fact, in classification. So what do we mean about that? Okay, so here, so that in this example, we want, in fact, to recognize if it's a square in the blue part here, or a triangle here, the red part here. So here we have two parameters, P2, so, and P1. This P2, for example, should be the rectangularity, and the P1 should be, for example, the circularity. And what do we do? In fact, so we have learned, so it should be, for example, not exactly what we obtain. So the problem is, if we want to separate here the space, it's difficult. Here, this position, in fact, it was a first example of a square. Maybe it's a perfect square. Here, that is a second example. So it's in our database, okay? But here, for example, it's a square, but with some noise on the square, okay? Some, maybe, for example, the coins here is not very perfect. So it means that the measure here is not the same, okay? Here, for example, again, it's a square, but with maybe another part of noise here. So it means that in the space parameter, so the blue shape here, so in fact, we see the squares. In fact, we can find this one, this one, this one, and they are always in the same category, okay? In the same way, we have the same problem with a triangle. So maybe here is a perfect triangles, but maybe this one, there is some problem here on the coins and so on. So it means that the measurements are different, and the location in the space parameter, P2 in regards to P1, so maybe it should be here, for example, this one, but it should be for a third one here, and so on, okay? So the problem is, as we can see, we cannot separate this space with linear classification. Because, for example, if I use a line here, okay, I have here a separation here. But the problem that I will have, so maybe I can go here and to add, excuse me, if it will not work perfectly. No, not with this one. No, it's here. Okay. Okay, so if I put separation here, so the problem is, if I put that here, so the problem should be here. Okay, I am here, but if I put my separation here, so the C1 class category and C2 category here, so it means that, okay, for triangle, it will be perfect, but sometimes I have learned that this one is a square object. So there is a mistake. So another solution should be to do that. Okay, maybe to do something like that. Okay, so if I want to do that, but I can do that. Okay, so it will be perfect for the square classification, because all the square will be recognized perfectly. But here, so with the triangle, so there were mistakes here, okay? So as you can see here, with linear separation, it's impossible to do that, okay? So the solution here is to use this one, and to use this one, so maybe I can come back here, okay. Okay, so is to read, in fact, to use this k nearest neighbors algorithms. So what do I mean? In fact, here I have a new measurement to do. I want to recognize this shape. The question is, that is a green position here. So the question is it a square shape or is it a triangle shape? That is the question. So what do we do? Is to, in fact, to use the first solution. So K, it should be, for example, 3, 5, 7, and so on. Okay, and in fact, we can look from this position and to select the 3 nearest neighbors. So if we do this one, as we can see here, so here we can see here, so we have here 1 time the square here and 2 times the triangles. And after that, we take the majority, and the majority here is triangle because I have 2 triangles and only 1 square here. So it means that the answer will be, in fact, k equal with k equals 3. So here we can have the as classification, we can have triangles. Okay. Now another example, if I take the 5 nearest neighbors now, so with k equals 5 here, so we have 1, 2, 3, 4. Excuse me, 1, 2, 3, 4, 5 here, and here the majority we have 3 squares and only 2 triangles, so the answer will be 5. Okay, so as we can see here with this example, so it depends, in fact, of the neighbors that we are using. So generally, we don't have in the example only 5, 6 example, we have 100 and 100. So generally with k equals 3, 5, 7, or 9, so we can have a good behavior and good performances of our classification. Okay, just to show you something here. Here, so we have a library in Python, as I explained before. So you can find some explanation about this one. So just to go to, I have to, excuse me, I have to go here. Okay, maybe if I can go here. Okay, that is just to show you some examples. So here in my slides, I gave a website, okay, address. Okay, so we can use this one. So with scikit-learn, and scikit-learn is, as I explained before, is in fact a library in Python. Okay, so that you can use. I will give you some example after that. And here, so that is an example of how to use this one. So here you have some explanation, and here we have, in fact, the Python programs here, so you can see by yourself after my lecture, and to examine this this kind of example. But I will speak about that after. Okay. 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 So okay. So that was this one. Okay. So now there are some other non-linear classifier, and some of them are very famous. The most famous is, in fact, maybe is a SVM. SVM means super vector machine. Okay, so in fact, it's a non-linear. Okay, if we consider here, as I explained before, linear classification. So here again, in this example, we have two categories or two classes. Okay, two categories. We have the category plus and the category minus. Okay, so here that is we have only two parameters in my example. Okay, and what we try to do, in fact, okay, so that is what we obtain with our databases. So in fact, this one was one example, here a second example, and so on. Okay, so we have several examples. So we obtain this example of space parameters. It's the same idea as I explained in my previous lecture for rectangular and triangle shapes. Okay, so that is this question is now how to separate correctly. So as we can see, and we have seen that also for the K and N. Okay, so here, so it depends of how we put this separation. So now the idea, so as we can see, so we do some mistake. It's difficult to do. Okay, so the idea, in fact, is to, to consider margin. Okay, and that is what we do with a super vector machine. Okay, so we do. Okay, we have the theoretical line separation here. It's linear. But in fact, as we have maybe on the border, we can have some mistakes. Okay, so that the idea is from this ideal separation, we put a margin. So that is what we put here in blue, here and here. So here, in this area, in fact, that is in fact the separation part, okay, and area. And in fact, what we can affirm here is if we are here, we are sure that it's a category plus. If we are in this part, we are sure that it's a minus part, okay, or minus category, excuse me. And here, when we are here in this part, so that is the border separation. So with a super vector machine, so we can have a larger part here, for example. And again, here, so it means that if we are here, we are sure. If we are between here and here, we are not sure. Okay, so it should be okay. So we don't know exactly. And here, this one. And using radial basis function, what we can say is if we have here, in fact, an exponential or in fact a Gaussian shape. Okay, so we can say that here we are at the maximum here and here, so we can have, in fact, a separation like that. Okay. So with that, so we can have some example. So that is an example, a very famous example. So that is the second very famous example that we can find in machine learning. The first one, excuse me, was in fact for handwritten digit categorization. And here is the flower classification, which is a very famous example. Okay, so I am not very familiar with, not a specialist in botanics, okay, in flowers, but what I know, what we can know is that here we have the petal for any kind of flower, okay, so we have the petal, and for each flower we have a, here for each, which is a sepal, okay, and in fact, okay, we can, here we can say that it's a specific iris flower, okay, with a yellow color, okay, it's fine, it's easy to do that, but now we can find different flowers, different families of flowers with the yellow part. So to separate and to classify exactly what is exactly this flower is in fact to calculate in fact the shape, or to classify the shape of the sepal which is here. And in fact, what we do, we can, with image processing, we can measure the length of this sepal, okay, the number of pixels in the length here, and the width of the sepal here, okay? So in fact, we can extract from this image two parameters, the length and the width of the sepals, okay? So with that, so we can, in fact, classify exactly with a supervector machine, okay? Here, the kind of, in fact, of flower what we have. As I explained here, so we can measure, in fact, the sepal width and the sepal length parameter. And depending, in fact, of what we have, we can have different results, as we can see here. So here that is with linear, only linear space. So because here, in this example, we consider 3 categories, okay? Flower 1, 2, and 3. And flower 1 is a blue part here. Flower 2 is a red part here, and flower 3 is a white part here, okay? And depending of as we can see here with supervector machines that we can use here, so we can have supervector machine with RBF, okay, Gaussian function as I explained before, and also with polynomial degrees, in fact, okay? So as we can see here, with the blue part here, so it was linear, okay, supervector machine. So we can see that this one, there is a mistake here, okay? And because the blue part here has not to be here, but has to be here, okay? So, and here, as you can see, with this separation, which is non-linear, here we can see that the classification will be perfect for the blue family, okay? And here, so there were some other mistakes, but we can decrease with this one the number of errors that we can have. So it depends of the applications that we can see here with RBF or polynomial. So it depends, in fact, of the applications that we can use. Okay. So again, there is an example of, excuse me, because here I have, no, it's not here, so I will explain that after. So again, we have a specific library in, we see that in my demonstration after. So, excuse me, okay. So here, and we have a Python program, okay. So we have with a scikit-learn library, we can use also this same kind of example. Okay. Okay, that is what I suggest here. So with scikit-learn, so we go now with this one, so we can find the classifications. That is what I explained here. So we can find the SVM, as I explained here. We can have also the k nearest neighbors, as an example I explained here. Okay, so if I use scikit-learn here, excuse me, so we can find that here. Okay, so I can see that. Okay. Okay, so that is what you obtain. Okay, so that is a scikit-learn.org, which is an open, it's open, okay, open source languages, okay. So here, as I explained in my slide, so we can have different possibilities, okay, with this scikit-learn, and I suggest for you to examine this library. So as it's written, it's machine learning in Python. Okay, so you can use this one. And as I explained here, so we have the SVM. Okay, so that is the example that I have shown. So again, you have some program example, so you can execute by yourself all this one. Okay, you have the same also if I come back here. So with this one, I have, for example, the neighbors, nearest, for example, the KNN. Okay, as I explained before. Okay, so you have some explanations and so on. So you can see that by yourself. Okay, so as you can see, you can find some examples here that is of, in fact, face, in fact, expressions. Okay, so you can see this one and so on. So here, that is the explanation of what we can do here. So I don't read this one today. Okay, so you can read that by yourself, but that was just an introduction how for you to go to this one. Okay. Okay, so this is what we can use. So we have a lot of resources to go further directly. Okay. Okay. Before to continue and to go now in artificial neural network, I would like just to show you again some examples of Python program that I use here. So here, that is what I can show for you. Okay. Here, that is again some examples that I want to show. Okay. Okay, so that is the first example that I explained before last time. Okay, so Professor Sarifuden told me that now you have this example, so I hope that you can test this example now. Okay, and as I explained myself, I am using the Spider graphic user interface. Which is very, in fact, which is very close to the MATLAB environment. Okay, and here that is the first example that I would like to comment again. It was it's the example of image processing here. Here in this example, just I would like to execute my program here. Okay, that is what I have shown the last time here. So this one is with this program. So I use, in fact, this one. So it's I open this image, which is an image of it's a color image of a dog, as you can see here. Okay, so that is what I do here. First part of this of a Python program for any kind of Python program is like in a C++. You have to declare, in fact, the libraries that you are using. That is the only difference with MATLAB. Generally, in MATLAB, when we are using MATLAB, so we have already the toolboxes which are installed, okay? But we have to pay normally, or the university or your company has to pay, okay, for that. And here it's free. Python is free. And so, but the only difference is as it's free, okay, we have to do more things. So like this one, so you have to declare the libraries that you are using. Okay, so for example, the PIL library, in fact, is used for image accesses, how to read or how to open an image and so on. So you are using the image, okay? This first library. The second one, which is very useful, is matplotlib library. Matplotlib helps the user to draw some images, but also some lines, some, in fact, to draw some examples, some figures, and so on. Okay, so it's very useful. Here, NumPy, as I explained, because as in image processing, but also in machine learning, and after, as we'll see in deep learning, we are using, in fact, matrices, because an image is like a matrix, okay, in a mathematical point of view. So here, so NumPy help us to use matrix and so on, and also to all the numerical calculation, okay, multiplication, division, and so on. And here, that is a specific, in fact, tool library is a scikit image, okay, which is this one, which is very useful also. Here, I don't use OpenCV as I explained before. So, in fact, it's like OpenCV. Okay, so in this example, just to remind you, here, so I am reading the image. The name is Beagle PNG. And here, I transform this image in a matrix here, okay? So here I have, here like in MATLAB, so I can examine the contents of the variables. So here, so I have the EMG, okay? So EMG in, which is EMG in, which is here. So it's an array, it's in the format image. So we cannot, we can just, in fact, represent, in fact, the image, okay? We can show the image, but we cannot, with this format, do some calculation, some processing inside. So we need to transform this one in an area, in an array. An array means that we have a matrix, okay? So with that, we have EMG. So EMG here, so we can see that this image is 336 rows and 500 columns. And here it means that we have, for this image, it's an RGB, red, green, and blue, in fact, image, okay? And channels, so we have 3 channels. So it means that we have 3 matrices in the mathematical point of view. As I explained before in my previous lecture, here I can extract from this one each channel, blue, green, and blue, blue, green, and red, okay? And I can transform that also. It's an in fact integer on 8 bits, and it means that we have unsigned, so it means that it's only positive integer on 8 bits, so it means that the value will be in between 0 and 255, okay? So as we want to do some mathematical operations, so we have to transform these integers in float, okay? And that is what we do here. So that is what I have. After that, I can calculate, in fact, the histogram of the gray levels of the image, okay? So the idea is to count the number of times that I have the black gray levels, white gray level, and also between 0 and the maximum, which is 255. How many times, for example, we have the gray level 10, and so on. That is what I do here. So I calculate this histogram. Here, that is just to show you, in fact, how to declare a function. Here, it's a function inside the program. Here, so here, that is this function. So maybe now you begin to be familiar with this one. So here, what I do, so I declare my here my function. So I can now call this function. So I calculate this table, in fact, because histogram is like a table, okay? And when the in fact representation, and here, so I calculate the histogram of this variable. This variable is a image here, okay? So that is what I obtain here. So when I go to the plot representation, so here, so I have the image in gray level, and here, that is the histogram that I obtain here. Okay, with plot, I can represent that directly. So as you can see, so here I have some values as a black value because 0 is black value. 255, it's a maximum, is a white value, and between them we have gray levels, different gray levels. So for example, here around maybe 190, so I have a clear value or white values, and maybe it's something like this one. So maybe we are in this area, and when we have this peak here, so it means that we are maybe at the value gray level equals 10 here. So maybe it's something like here in the dog here, okay, and so on. So with this histogram, which is in fact 1D signal, in fact, okay, so we can represent some, we can have some information about that. Okay, and here we can draw, in fact, the result using the, in fact, the PLT library, which and PLT, in fact, that is, in fact, the matplotlib pyplot. Okay, and here that is the alias that I am using. Okay, so that was the first example that I wanted to show today. Okay, and how to use it, to use that. Another one I don't use this morning, maybe should be to represent, okay, the SVM here. So with SVM, we are here, okay, and I can open this one, which is the example that I use here. So we can access to this one here. Okay, so here I have this one, and as you can see, maybe here, I am working on the flower application, example of flower application. Okay, it's here. Okay, and here, so I am using the, in fact, this databases from Iris. Okay, so if you look at that, so here you have some value, and in fact, what means this, in fact, this table. So here is, as I remind you that we are using for the flower recognition, we are using the sepal dimensions, so the width and the length of the sepal. Okay, so here, in fact, we have a lot of value here. So maybe I don't know exactly, but maybe 100 or 200 values. Okay, and here we have a couple for each flower. We have the measurement of the length and the width, in fact, of the sepal. Okay, so here, for example, we have a length of 5.099 and so on. Okay, and here, so that is the length in pixels, and the 3.5 is the width of the sepal, and so on. Okay, so we can have for all these ones, so we can have different values. And for example, the first group corresponds to the first category of flower, the second, and so on. Okay, so that is what we use to learn our, in fact, the classifier to dedicated for the flowers, iris flowers classification. Okay, and here that is what I have here. So we know that for the first group here, from here until here, so that is a category 0. So all the first part that we have seen just before, in fact, that is the category 0. On the middle is the category 1, as we can see here, and at the end we have the category 2. Okay, so when we are using that in my program now again, so I come back here, so that is this one, and in fact here I can read, so that is all the program, so we can obtain, so you have that from what I sent for you, okay, but you can obtain directly this example from the scikit-learn open source access, as I explained before, so we can obtain that directly. But as you can see here, I access to this iris data.txt as I've shown just before here, So that is the data, and here the target, in fact, the category that we have. Okay, so we use that inside our program here, and in fact, we can just calculate here for the SVM. So we can see that directly. Okay, so we are using this one. So that is what I've shown on my PowerPoint, okay, before, so that we obtain directly with this example what we have shown in my PowerPoint before. So you could use that by yourself if you want. Okay. So that is the end of the first part of my presentation. Now we can go to the second part of my presentation now. Okay, so I close this one. Okay. Okay. Oh no. Okay. No, it was not. Okay. Okay. So I have to open the second one, which is this one. Okay. Okay, so during the second part, I will speak now in more details because about artificial neural network. In the previous part, as I explained, so we have different classifiers, okay, linear, KNN, and SVM. So now let's see another way to do classification. And now we'll go to artificial neural network. So during my first lecture, I gave a long introduction about the artificial neural network, about perceptron and so on. And now I will go in more details about that. So first, in fact, general information is in fact there was different definitions. So we are speaking about connectionism, because in fact, artificial neural networks, so inside the artificial neural networks, so we have neural networks, okay? And in fact, the definition of artificial neural networks is in fact the modeling of the human brain. So it's the mathematical modeling of the human brain. And the scientific word for that is connectionism. Connectionism means that we have all the neurons, we are connected all together. Okay? And that is what I explained here. And in fact, the origin from this, in fact, this area of the scientific area comes from, as I explained, some computer scientists who tried in the last century to copy, in fact, the behavior of the human brain. Okay, so the first objective or first target area was, in fact, to study and to model, in fact, the behavior of the brain. Okay, how works the brain and so on. So they did some simulation for that. Okay, so and there is again some very important development about that. But here, in the context of my presentation, is not what I want to do. In fact, I want to use, in fact, artificial neural network to solve complex problems. And when we speak now, right now, about artificial intelligence, about deep neural networks and so on, so in fact, the most of the applications concern, in fact, the solving of complex problems. The question is how to recognize a flower, how to recognize the handwritten text, how recognize a specific face, and so on. Okay, so is how to classify different objects that we can see in an image. Okay, but it's not only for the image, as I explained, but here in my lecture I focus on the image. Okay, let's see now some definitions about, in fact, how works. Excuse me. I have some. Okay, how works in fact how we can model the brain. Okay. So first thing that we can say is, in fact, if we have here the, in fact, that is a brain, the cortex, in fact. And as we can see here, I focus on image processing, okay? So, or image analysis. So here we have the biological retina. So here, the time for the retina, which receives image information from outside and to go to the closest neural network, it takes between 20 and 40 milliseconds. Okay, so we have here a first step here, which is a GN, which is the first layer of neuron, a second layer of neurons here, and so on. And we have here the high-level neurons here. So as we can see here, it's a feed-forward processing. So it means that we have the information which comes from the outside, which arrives here on the first layer. From the first layer, we go to the second layer here, and so on. So as we can see here, we don't come back here. So we have, it's always from here to here, from here to here, and so on. So it means that it's a feed-forward processing. Okay. And to do all the calculation, as you can see here, it will take maybe, for example, to recognize different objects or to have some actions. It takes between 150 milliseconds and 200 milliseconds. So it takes, it's not in 0 milliseconds, so it takes maybe until 200 milliseconds. Okay? Okay, so, but for each step, it takes few milliseconds. Okay, see, okay, the amount of all that is 200 milliseconds, but in fact, the time step is a few milliseconds. Okay. Another thing is for each neurons, we have information which is spikes. Okay, so some information. But what is very interesting in our brain, in fact, we have a lot of neurons, and it means that each neurons process few informations. That is the reason why we can do a lot of things and to process a lot of things to recognize. Okay. The second definition is concerning the neurons. Always a problem with that. Okay. So as we can see here, we have in fact the neurons directly. So neurons is inside here. Neurons is inside this one. Okay. So we have a connection between each neurons. Okay. So in fact, we receive the electrical informations. Okay. Each neuron receives different electrical signals. Okay. And after that, it sends the information to the axons. Okay. And the connection between two neurons, so between axons and dendrins, in fact, the name is synapses. Okay. And as I explained in my introduction during my first lecture last time, I explained that we have, in fact, synaptic waves. So it depends, in fact, the influence of each synapse. Okay, we'll see that after. What is very interesting also is the number of neurons that we have in the brain, the human brains. So approximately we have 100 billions, okay, of neurons. So it's very huge. So if we compare, in fact, to a processor, it means that inside our brain, we have 100 billions of computer, okay? But it's very small computer because this computer is similar to a perceptron, but in fact, we have 100 billions. We don't know any kind of computer right now which is able to do that, okay? So, in fact, the human brain is very performant for that. And each neuron can communicate with a lot of neurons, and we have 10K synapses for each neurons. Okay, so it means that inside the brain, so we can find, in fact, 10 power 15 synapses. In fact, inside the brain. So it means that it's very huge again. Okay. Thanks to the parallelism inside our brain, we can operate at 1 kilohertz. So it's very slow, in fact, in comparison with, for example, 1 gigahertz frequency in classical computer, okay? And to do all these operations, it takes only 20 watts to do that for 100 billions of computer. If we had to do that with a computer, it should be like a nuclear plant to do that, okay? So it will be tera and pentawatts or something like that. If we had to do that with software, with a computer, okay? So it takes only 20 watts. So it's very efficient about the energy that we have, about the power consumption. Okay. That is just this number was just to tell you that, okay, with artificial intelligence, now we can do many things, but in comparison with human brain, we do very few things with artificial intelligence in regards to, in fact, to the human brain. But in fact, what we can say is with artificial intelligence, we can have very good performances for a specific task. For example, for flower recognition, okay, we can learn to our artificial intelligence to be efficient for flower recognition. So it will be very efficient to do that, but it will be not very efficient, for example, with the same artificial intelligence to recognize human faces, for example, okay? It works only for flower in this example. And after, for faces, we have to learn another artificial intelligence. So in other words, what I consider for each application, we have to learn a specific artificial intelligence. Just to remind you some, in fact, the historical summary, that is what I explained in my first lecture, but just to remind you. So, in fact, in the middle of the last century, so we have the introduction, in fact, of the formal neurons. In fact, it was a perceptron, okay? So with the arrival of Rosenblatt and so on, with some law to learn, in fact, the neurons, the formal neurons and the perceptrons. It was Ebb's law and also Widrow and Hoff laws, which are very famous for the perceptron. Okay, so as I explained before, and we see that again today, in fact, there was a problem with definition of perceptrons, and Minsky and Peppert have shown in this period that there was some difficulties with perceptrons, which was very difficult to apply these perceptrons, this artificial neural network, to real applications. So there was some problems, and during 10 years, a lot of researchers tried to find some solutions. And it was only at the beginning of the 1980 that Lequin and Holz have shown that it was possible to use perceptrons using, in fact, multiple layer perceptrons. Okay, and during, in fact, from 1980s and in fact 10 years ago, at the beginning of the 2010s, so exactly in 2012. So during, in fact, 30 years, a lot of people, and I was one of them, tried to use, in fact, multi-layer perceptrons, but in fact, during this period between 1980s and 1910, performances were not so good. And it was only from 2012 with deep learning, in fact, that the performances of the artificial neural network was efficient and able to use that in real applications. Okay, so in fact, there was, if I summarize, what was a first life of the artificial neural network was before 2012. Okay, so it was the first generation of artificial neural network. We are now in the second generation, and in the future we'll see maybe the arrival of third generation, but I don't know what will be this third generation right now. Okay, so just to tell you again some new definitions, to adding definitions. I explained that in my introduction last time, but again, the idea is when we have a perceptron, neural network, so we need to learn, in fact, the connection between each neurons, in fact, with the synaptics weights, so coefficients, so it's synaptic coefficients or synaptic weights, okay? So the problem is how to learn that. To do that, as I explained today, so we use, in fact, learning databases, okay? And we send a lot of examples and we learn, in fact, the artificial neural networks. That is what we do, in fact, with the learning base, okay? And so we know the input and the output. As I explained just before, these slides, in fact, I've shown the example with flower classification, okay? So we have the data, for example, the length and the width. I've shown that in the with my files just before. And also I have a second file, which is a category, okay? So I have, in fact, the input is values, for example, for the flower example is the input is length and width of the sepal, okay? And in fact, I have the example, which is the output that I have to obtain. The output is the category that I have to obtain, okay? And the test base, as I explained, so from the database, we extract 10%, around 10% of the database to do some test and to see if we have, in fact, a good solution. Okay, so that is some definitions that I explained. Another also definition, which is very important. In fact, we have two kinds of learning. So we have the supervised learning and the unsupervised learning. Generally, and that is what I will use with you, is the supervised learning. We know we are the professor, okay, so we know the solution, and we teach to the artificial neural network. We teach how to learn this solution. So we send a lot of examples, okay, and we say for each example that is what we have. We are in this category. So again, if I learn, for example, for the MNIST databases, so in fact the 10 digits, so I send a lot of times the 0 digit, and I say to the artificial neural network, it's a 0, okay? Again for the 1, and so on until the 9 digit, okay? So that is what what I explain, what I'm speaking about supervised learning. Second kind of learning is closest to the human brain behavior. In fact, we don't know exactly the solution. And in fact, we show a lot of times different examples, and that is the artificial neural network itself. We do some clustering. So for example, we send a lot of time 0, after 1, after 2, okay? we don't tell to the artificial neural network what is the category, but itself, he has to tell, okay, I don't know what is this shape when we send this shape, which is a 0, okay? He does not know it's a 0, but you see when we send this shape, is very different than the other, for example, the digit 3, okay, which is very different to the 0. So by itself, in fact, the neural network is able, in fact, to do some clustering. And here, for example, for the digit recognition, it can by itself, in fact, separate 10 categories by itself. And after that, we have to just to tell, okay, this cluster is 0 digit, the other one is 1 digit, and so on. Okay, we will not speak about that today, and not during the next lecture, but in the future, we can find more and more, in fact, artificial network, we will be able to do that, okay? So now, the problems that we can have either on supervised learning and on unsupervised learning, in fact, is over learning. And that is a problem, a general problem that we can have for all the learning that we are doing for artificial intelligence. If we send a lot of examples who are similar, okay, we can have overlearning. What I mean about that is, for example, if I want to send again the same, for example, when I was speaking about digit recognition, if I send always one example, if you remind, in fact, the one, it was like, in fact, it was like one with American notation, okay? And okay, in Europe, we don't write the one like that, okay? But we put this one and this one, okay? So if we learn a lot of times this example for the one, okay? And so it will be overlearning because we are able with this one to recognize only the one digit like that. And if I have something like that, okay, so it will be different for the artificial network, but the output has to be the same because this one and this one are the same. So that is what I explain when I speak about overlearning. If we send always the same shape for one category, we will be in overlearning. So we have to avoid this, this example. So the idea generally is to have a lot of different examples for the same category, and all these examples have to be obtained in different conditions. Okay? Okay, so that is when we say that it's stupidly learning, okay, when we do only the same example and we don't have the possibility of generalization. Okay. So we stay now in supervised learning, and the objective is to avoid the overlearning. Okay. So now we come back to the definition of the perceptron, and as I explained last time, so the definition of the perceptron is as you can see here. So here we have, I remind you that we can consider n input. Okay, this n input could be, for example, the features that I explained during my first lecture, excuse me. If I take the example of how to categorize rectangular and triangle shapes, we'll have only two elements here. So it will be x1 or x2, okay? But generally, we have more than two features. We have a lot of features, as I explained before. Okay. So what we do, in fact, we send each input element here to the same neurons here. And between each element in this neuron, as I explained, so we have the synapse here, and for each synapse, we have a weight or a coefficient. And the name of this coefficient is y1 here, y2, and yn here. Okay, so we have also the output. The output is O here, okay? And here we have also the bias or a threshold, which is theta here, okay? So what do we mean here is we calculate for each neuron, so this operation, in fact, which is the multiplication between this one and the input element, and so on. That is what I explained here. And if this summation is above this threshold theta, so we'll have the category 1, and otherwise we'll have the 0 category. Okay, that is the last time I spoke about on the output +1 and -1. Generally, we take that. We take +1 and -1. But sometimes we take also, it's a binary output. Okay, so it depends of what we want to code. Okay. So just to show you now how to learn this perceptron. So I explained with my hands last time how to learn the perceptron, but now I will show you what is this exact algorithms. So for that, we use, in fact, the withdraw-off algorithms to learn this perceptron. So in fact, first of things, so we have the databases. So I spoke a few times, or maybe several times about databases from this morning. And as we have seen, it's very important to select the good learning databases. Okay, so if we consider a mathematical point of view, so if the notation of this learning databases is S, okay, so I select in S, in fact, the vector input, x0, x1, xn, and so on. So for example, it should be the rectangularity, circularity, or if we consider the flower example, it will be, in fact, the width and the length of the sepal and so on, okay? And for each example, in S, I give a category, okay? So I gave a lot of examples about, some example about that from this morning, okay? And now the question is how to obtain the coefficient y0, w, excuse me, 0, 1, and so on. So the algorithm, that is the question, okay? So the withdraw-off algorithm is as follows. So at the beginning, we generally we do a randomly initialization of these coefficients. That is what we do in general, okay? And we repeat for each step, okay, these following operations. So we take a first example in S, in my databases, and in this example, I have the cowpole, so the input, in fact, which are the parameters, okay, or the features, and the category for this example. Okay, so, and we do, in fact, this calculation. So we do this operation. So we calculate the new synaptic coefficient, okay, with this operation. So with this, that is the corresponding output that I want to obtain, and O is what I obtain with artificial network, with the perceptron. As I explained also, so we can have some mistakes. So if C and O are different, okay, so I have, in fact, to calculate the new coefficient. If they are equals, okay, C equals O in this case, so the coefficient stays at the same value, okay? So in fact, we change these coefficients when there is a difference between, in fact, the target, the desired output, and when I have a mistake with the output I obtain with, in fact, the artificial with the perceptron, with the artificial neural network. Okay? Okay, so let's see an example now, a very simple example, which is, in fact, what we could do, in fact, with very simple logic operations. So one of them is OR functions. As you know, when we have the OR function, so we have two inputs, A and B. And when we have 0 and 0, so the output is 0. When we have 0 or 1 is 1, and so on. Okay, so we have the truths table, which is here. And the idea should be to show this different example and to find, in fact, the W0, 1, and 2. Okay, and we want to calculate this coefficient. So to find these coefficients to be, in fact, efficient to execute these functions. Okay, that is what I explained here. So here, what we put, here we, on X1, we put, for example, the A input, and on X2, we put the B input, okay? And we try, in fact, with this one, and on the X0, we put 1, it's a constant, okay? Okay, so we begin with that. So what we do here, we calculate with the Widroff algorithm, so with this one, we calculate, in fact, this one. So, excuse me, here, entrée means that it's input, okay? And étape means it's a step, okay? So here, what I do the initialization. Normally, it has to be random. So here it's random. So the value that I put here is 0 for the first coefficient, 1 for the second, and -1 for the third coefficient. Okay. So we begin with this one. So that is the initialization step. So 0, 1, and -1. Okay, so on the input, as I explained before, on the input, okay, so I have 1 here. X1, for example, is this one, and X2 corresponds to the B input. Okay, okay, that is what I have here. So the first combination that I have on the input here is 1, 0, 0. Okay, so it means that I have now to calculate the corresponding output here. So what I have to calculate, in fact, is the multiplication between this one and the corresponding coefficients. So this one is a 0 input, the input 0, x0, okay? And so I multiply 1 by this one, so it means that it's 0, okay? Plus this one multiplied by 1, so 0, and so on. So the output of this one will be 0. So this operation will be 0, okay? The output is if this value is above or equals to 0, okay? So it will be, in fact, positive, okay? No, excuse me, it will be 0, okay? So the observed value, which is in fact the output of the neural of the perceptron, in fact, which is here, okay? So it will be 0, excuse me, d'accord? Because we are more than, we are equals to 0, okay? Now, so it means that C minus O equals 0. So we don't have to change the coefficient which is here. So these coefficients will be the same as I explained here. So it means that the coefficients for the next step will be 0, 1, and -1. They are the same. Okay. So now we can calculate the second one. So in example, second step here, and now the input is 1, so it's a constant, but we have 0 and 1 input. So here, that is a 0 and 1 example. Okay, so normally I have to obtain 1 at the output. Okay, so 1 on the output, that is what I obtained here. The observed value is the same as the previous one because we have again this one. So it means that we'll have 0. Okay, so it will be 0. So it's different. So we have here C minus 0, it means that it will be 1. So we can reactualize the new value of the coefficient for this one. So we obtain here, so this value, because it will be 0 plus 1 by 1, okay? Okay, it will be this one. Here it will be this one, and so on. So it means that the new coefficient will be this one, and so on. Again, we send the new example on the input here, and we obtain all this one. Okay, so thanks to this one, we can learn at the end why 0 equals 0, 1, and 2. Okay, and we obtain, in fact, directly the value to learn the Earth function. So if we put 0, 1, and 1, so it means like this one. So it means that we can calculate directly the good solution. Okay. Just to give you now the examples that the example of Python program. So here I give you an example of this Python program. So here, so we have the input values that I want to obtain. So as I explained before, we can have, because we have two input data for this logical function. So we have 4 combinations. So here we have the A equals 0, B equals 0, here 0, 1, and so on. Okay. Here that is to learn, for example, the n function. So here with the n function, so we know that when we have this combination, it's a 0. When we have 0 and 1, it's 0, and so on. And we have only 1 when we have 1 and 1 here, which it means it's this one. Here is the logical OR function, as we have seen in my previous slides. And another example should be, for example, the XOR function, which is this one. Okay, so you know that, I imagine now. Okay, here we can put here not 1 as I explained before, but for example, here I put -1. Okay, and the coefficient, the epsilon coefficient, should be, for example, here 0.7. In my previous example, I put here epsilon equals 1. Okay, but here I put a different coefficient, which is this one. The bias here, we don't put here 1, but I put 0. I don't remember, -1 here. Okay. Okay. Here I've put my initialization. As I explained before, it's random. So, for example, here, because the question is how to calculate, in fact, the 3 weights which are here. Okay. So what I do, so I calculate the, in fact, for each, so I apply the withdraw-off rule here, and this withdraw-off rule. So I do, in fact, the calculation which is here. Okay, just I will not speak about that today. So here that is a non-linear function that I obtain here, but okay. And after that, so I can calculate, I can do that for different steps. Here I consider 1K steps. Here I had only one. Here I had only 10 steps. But in my Python program, I use here, in fact, 1K steps, as you can see here. So with that, I can do directly, but with automatic way, all these calculations that I have here, and we can obtain at the end, in fact, directly the good weights that I want to obtain. So let's see now my example of my Python program. So I send for you this Python program. Normally you have this program directly. So I have this one here. So I have to come back here. Okay. Okay, so now let's see my example. So it's a perceptron. Okay, and with this perceptron here, so I would like to reset my function. Okay, okay, so you have 0 here. Okay, and okay, that is a program that I have shown for you. Okay, here that is I would like to, that is exactly the same program that I comment in my previous slide, and here I have the my program, and I would like to learn, in fact, the logical end function. Okay, so I execute my program now. That is the same that I comment before. Okay, and okay, I did that. I obtain directly the values of my weights here. So I have my 3 coefficients directly here. So it's very fast. And here I have here, in fact, the errors that I obtain. So as you can see, at the end, the error that I obtain when I have 1K iterations, okay? So 1K steps, okay? In fact, at the beginning, I have a large error here, and it decreases very fastly, okay? And at the end, I have a convergence here. If I look to the error that I have, so I have here this one, and as you can see at the end, it's very slow. It's the value that I obtain here. So as a 1K at the end, so you can see that I have here, and at the end here I have a very small error like this one. That is what we can see here on the plot. Okay. Okay. So it means that normally. I have learned my neural network here, my perceptron for the end function. So now I can test this one, okay? Because in fact, at the end, I store all these coefficients are stored in a CSV file, okay? So I have here the CSV file, okay? Well, in fact, it's the weight file, which is here in a CSV format. Okay, so now I can read this one, okay, and now I can test the outputs that I have to obtain. So now, in fact, what I do, I read my weights file here, and here after I test for the 4 combinations, possible combinations, I test my perceptron, my neural network. So that is what I do now. Here, so okay, so here for the first combination I have 0, 0, okay. The output was negative, okay. That is the summation of the weights multiplied by the each input, and for all the inputs, all the weights, I do the summation, and the summation was minus 14.49 and so on. Okay, so it's minus, as it's minus, okay, so it means that, okay, my threshold was 0, okay, so if it's less than 0, it means it's false. If if it's positive, it's true, okay? So it means that when I have 0, 0, I obtain false. When again I have 0, 1, it's false. 1, 0, it's false. And now 1, 1, as you can see, it's positive. Here it's true, okay? So now I have learned this perceptron for the end function. Let's continue now again. Let's go now to the OR function. So I have to comment this line here. So now I come back to my learn program. Okay. So now I would like to learn the OR function. So, okay. So the OR function, as you can see, the values are different now, and the error curve, we can see with the error curve that the convergence is faster. Okay, so the beginning, so we have a huge error. Okay, and here we can see that after maybe 10 or 50 steps or 50 iterations, we can see that we have a good convergence. Okay, so that is the new value for the weights for my perceptron, but using the same architecture of the perceptron now. Okay, that is just a parameter which have been changed. So now let's see the results here. And if I execute again this program for this one, it's the same program, okay, but with different weights. And let's see the results. Okay, so here now I send the 0, 0 input combination. It's negative, results false. But for the others, we can see that the OR function, we can recognize the OR functions. Okay, so with that, we can see it's perfect. So we can learn very easily these different examples. Okay, it works very perfectly for that. But now, let's see now the third example, and we'll see that it does not work for the third example. Here, I would like to learn for the XOR function. I remind you that for the XOR function, so here, so the output will be when we have 0, 0, it's the same, so the output is 0. When I have 1, 1, the input are the same, so output is 0. And when there are difference, the output are 1, okay? So that is what I learn. I do that, okay? And as you can see, there is no convergence with my, in fact, with my learning, because after 1K steps, okay, the error is always high, okay? And it means that we cannot learn directly for the XOR function, with only one perceptron. We can check that, and we check it's it's not working correctly. We do that to test that. So as we can see here, for example, for 0, 0, we obtain true. It's false because normally it should have to be 0. False, excuse me. Okay. Here it means that it's true. Okay. In this case, it works. But here again, there is a mistake because here, as we have a different input, so normally we should have the true output. Here, the output of the perceptron is false. So in this case, we can see that we cannot learn with the perceptron the XOR function. Okay, so there was some explanation about that, and that is what I will explain in the next lecture, because here that is what I have shown. So I come back here. So here. So that is what I explained. That is what I have shown here. Okay. Okay. And the problem is, and that's the reason why it works for the AND and OR functions is because, in fact, as you can see, it's a linear possible separation. Okay. But for the XOR function, you can see that it's not linear. Okay. So the solution for that is to use a multi-layer perceptron. And we will see that during the next lecture, which will be, if it's okay, next Friday. Okay, I would like now to thank you for your attention, and I will speak with you during the next third lecture. During the next lecture, because I have to stop my presentation and discussion because I have another meeting now. But for the next and third lecture, I will take time to discuss with you and to answer to your all the questions for the 3 lectures. So thank you very much, and see you with Zoom next Friday. So good. So goodbye. Pour Sari, c'est OK?
Oui, c'est parfait, Michel.
OK. Okay, so terima kasih for all of you. Okay, and see you by Zoom next Friday. Okay.
Thank you, sir.
Thank you, Professor.
Merci beaucoup, Michel.
Thank you, sir.